Yeah. So Tuesday we'll have a quiz coming Tuesday. Okay. Third quiz. And anything else? Yeah. So that's it. Yeah. So the coming Thursday we'll have the third quiz. So let me begin the lecture. So last time we talked about a little more about linear maps. So for instance, we showed that this set of linear maps between two R modules is an R module. So home RMN is an R module, and we showed that end Rm is a set of endomorphisms of M, that is our linear maps from M to M, is an R algebra. So we showed that it's a ring. Yeah. So in fact, it's an R algebra, which means that it's a ring, and there is a ring homomorphism from R to end Rm. So we didn't show this ring homomorphism, but I can tell you what this is. So here R will go to, what should it be? What should,
sir?
Yeah.
Sir, can you see the chat?
What is it? Tuesday. So coming Tuesday will be the quiz. Okay. So what should be the map from R to end Rm? What should be the ring homomorphism? Can you make a guess? R should go to which endomorphism? Yeah.
Multiplication by R.
Multiplication by R. Yeah. So maybe we call it mu R. Yeah. Multiplication by R from M to M, which sends little m to R times M. Yeah. So it's basically a scalar multiplication of the identity map. Yeah. So remember, given any homomorphism from M to N, you can multiply that homomorphism by an element of the ring and get a new homomorphism. So here is just multiplying the identity map by R. Yeah. So you can think of it that way. So this you can check is a ring homomorphism, and this is what an R algebra means. Yeah. R algebra is a ring together with the ring homomorphism from R to ring A together with the ring homomorphism from R to A. Okay. So we saw that and Rm is indeed a ring. And then we talked about generating sets of for R modules, and in particular, finitely generated modules are finitely generated R modules are those are modules for which we have a finite generating set. And then we also talked about free modules. Yeah, so free modules are free R modules are those R modules for which we have a basis. So it has a linearly independent set, and yeah, so it has a linearly independent generating set. Yeah, so that's what then you call it a free R module. And we saw that any finitely generated free R module, finitely generated free R module is isomorphic to isomorphic as an R module, that is isomorphic to R power n for some n. Yeah, and this n is basically the length of the basis. Okay. So I mean, maybe in constructing R power n, this next statement we used implicitly that if M and N are R modules, then M dx n is also an R module. Yeah, and via the scalar multiple component by scalar multiple. Okay. So this is where so we ended at free modules, and this is this additional thing. Yeah. So any questions so far? Or any questions from the last lecture?
Excuse me, sir.
Yeah.
So over here in this ring homomorphism,
Yeah.
Can we comment anything about its injectivity or surjectivity based on the nature of M? And R, of course, R and M together.
Yeah. So so it may not be injective and may not be surjective. So it depends upon M. So for instance, yeah. So maybe we'll do one example. It's a good idea to do some examples. Yeah. So maybe let's look at this guy example. So so let's take R to be Z. Yeah. So this already gives us a bunch of, so, and M to be some module. Z, so if I take Z mod NZ, some torsion module, it will tell you it can't be injective, right? So maybe Z mod 5Z. Yeah. Then what is and ZM? What is this?
It would be again isomorphic to Z mod 5Z.
Yeah, so it is a set of all maps from Z mod MZ, Z mod 5Z to Z mod 5Z. Yeah, so this is going to be this is and Z linearity doesn't impose any condition. So basically, you're looking at all group homomorphism from Z mod 5Z to Z mod 5Z. Okay, and that's basically isomorphic to Z mod 5Z. Okay, so maybe I'll so maybe I'll write it this way. This is same as, so maybe first thing is an equality. Home Z mod 5Z, Z mod 5Z, and I mean, you can put a Z here, so it doesn't change anything. And this is isomorphic to Z mod 5Z. What is the isomorphism?
F going to F1.
Yeah, so you can take F going to F1. Evaluate it at F1. Yeah, so this will and this evaluation map at F1 is going to be a linear map, right? Because it's additive, obviously. F plus G goes to F plus G evaluated at 1, which is same as F1 plus G1. And scalar multiple also is okay. So it is an R-linear map. And yeah, it's going to be surjective because 1, you can send it to any of these guys. Yeah. So so if you, meaning it will give you an R module homomorphism, and it is also injective. So if F goes to 0, that means F1 is 0. So if F1 is 0, F has to be, so F2 will be 0 and so on. So everything will be 0. Okay. So so this is so of course then the map from so R to and Z mod, or maybe I'll just write it this way, Z to Z mod 5Z. So where does this go? So this, so if you, and then maybe compose this map, yeah. So you can check that 1 goes to 1 bar here, okay. So, but anyway, I mean, even if you can't verify this, you can, you know, that it can't be injective, yeah? Because this is infinite, this is finite. But you can check that the composition is indeed this. Okay, so here 1 goes to scalar multiple of the identity, and then you, that scalar multiple will take it to that. So 1 will go to identity, and identity will go to 1 bar. Okay, because that is 1 evaluated, identity evaluated at 1, which is 1. Okay, so this is far from injective, and if you take something reasonable, then you will get injective. So for instance, if you take vector, R is a field and M is a vector space, then this is what is end? Yeah, so maybe R equals Q and M equals Q power N. Then what is end? And M. What is this?
N cross N matrices over Q.
Yeah, so it is, you can think of it as N cross N matrices over Q. Yeah, so, and what is the map from Q to, if you chase down this diagram, what will you get? Any guesses?
Diagonal matrices with Q on the diagonals.
Diagonal, you can't get scalar multiple. Yeah, exactly. So you take a rational number R, it will go to R times identity. Yeah. I mean, because R goes to, so that is the map, yeah? A scalar multiple by the identity map. Yeah, that is what we realized in this example. So this is what generalizes. Okay, so here, of course, it's injective, but not surjective. Yeah, so it need not be surjective, it need not be injective, and it need not be either as well. Yeah. So I mean, here if I take M to be Z mod 5Z square, then you won't get either injective or surjective. Okay, so it can be any map, I mean, you can't control much about it in some sense. Okay, any other question? So in fact, maybe I'll, since we are already here, maybe I'll state some facts, and maybe you can, maybe some of them I will assign as homework. So M and R module, then home R-linear mass from R to M is isomorphic to, what should it be? You can maybe guess from here, from this one, from this one. This will be the map. So what should it be?
M.
M, yeah. So F going to F1. If you do that, then you will see that it's actually isomorphic to M. Okay. So this is the first fact, and then maybe another thing, M. Yeah, so I think this is also okay. M and K are modules. Then home M n plus K, set of all linear maps from M to N plus K is isomorphic to home M n. So if you take a linear map from M to N and then a linear map from M to K, then you can consider the pair of those maps, and that will give you a map from M to N plus K, and conversely. Yeah. So if you have a map, so you project onto N and K, and that determines, the two projections determine the linear map. You can put R everywhere. So as I said, sometimes when there is only one ring, people drop R. So, okay, and similarly in the first coordinate as well. Okay, giving a map from M plus N to K, same as giving a map from M to K and then to K. and home m plus n to k is isomorphic to home mk. I suppose this is okay. Yeah, if you have a map from m to k and map from n to k, then you can say what the map will be from m plus n to k, and conversely. So note that these are R-linear. So these isomorphisms are R-module homomorphism. So left-hand side is an R module, right-hand side is an R module, and this is an isomorphism of R. Okay. So any questions? Okay. Maybe I should say a little bit about free modules. So free modules, so finitely generated free modules are R power n. We won't discuss much about infinitely generated modules. So let me not get into that discussion. So we already know that there are many examples of modules which are not free. For instance, m over, so here z mod 5z over z is not a free module. But it's not just because there is some torsion, yeah, because I mean it gets 5 kills this module, but there are some other reasons as well. So for instance, you can take q over z, yeah, so q is an abelian group, so automatically it becomes a z module. Q is a z module, but it's not free. Yes. And it doesn't, I mean, you can't kill any element, yeah. So take any element r of take any element r of q and take any element n of z. So n times r is never 0. So it's a reasonable module, but it's a z module which is not free, which is so we'll talk about torsion free later on. So torsion means something which is going to be killed by some element. So this is, so Q is a torsion free Z module, but which is not free. Okay. But we'll see that. Yeah. So I don't know if this is in the syllabus, but maybe it is. So I'll see whether. Yeah, this should be, so maybe we'll do the structure theorem. So in particular, we show that finitely generated torsion-free Z module is actually free. Okay. So finitely generated torsion-free abelian group is Z power n. So I don't know if have you seen this result? Torsion-free abelian, finitely generated torsion-free abelian group is. Have you seen structure theorem for abelian groups?
No, son, was not taught in Algebra 1.
So it was just hinted by Professor Nayak.
Yeah. So anyway, I think we'll see this in this course. Yeah. So no issues. So this also reminds me of one more example before I get to this correspondence I want to talk about. So so M is an R module where R is some commutative ring with unity, and say S is a multiplicative subset of R. Yeah. Then oh, okay, I haven't talked about SN. Yeah, never mind. So this localization of modules I haven't talked about at all. So maybe we'll not discuss this. Yeah. Oh, what I can say is that yeah, but I have talked about this thing. Yeah. So R's a commutative ring with with unity and S a multiplicative subset of R, then S inverse R is an R module. Okay. So in fact, so maybe this is not very interesting if I check once I tell you the following result. In fact, slightly more general, phi from R1 to R2 is a ring homomorphism. So ring homomorphism between commutative rings with unity, that is, yeah. And hence 1 of R1 goes to 1 of R2. Then R2 is an R1 module, is naturally an R1 module via, so what should be the scalar multiplication? R1 dot, R1, so R1 is an element of R1, R dot M maybe I'll say. What should be R dot M? For okay, for R in R1 and M in R2, R dot M, what should be its definition? Scalar
phi r times M.
Phi r is some element of R2 and you can do the usual multiplication in R2. Yeah. So, yeah. Is this clear? Maybe I'll just emphasize this multiplication in R2. Yeah. Okay. So that way you can see that S inverse R is going to be an R module because you have this natural map R going to R over 1 from R to S inverse R. Yeah. Okay, good. So this is okay. Okay. Any questions so far? Okay. So so there are no questions. So now I'll relate two concepts. Yeah. So one side we can think of so let R be a ring. So that means commutative ring with unity. I mean, some of these statements are true in slightly more generality, but let's not worry about it. I mean, whatever is true, you can generalize easily is generalizable, and you can probably figure it out yourself when needed. Right now, it won't be needed. So R is a commutative ring with unity, and MB at R and MB an Rx module. Okay. So Rx means polynomial ring where Rx is the polynomial ring over R. Okay. So we want to understand this. Okay. Yeah. So we want to understand. We want to understand it in somewhat simpler, somewhat different terms. Yeah. So so let me try to see what data this encodes. Yeah. So of course, since M is an Rx module and R is a subring of Rx, then M is of course an R module as well. So this also we saw some time back. Yeah. So then note that M is also an R module. Yeah, since R is a subring of Rx. Okay, and we but of course this loses some data. Yeah, so we don't know how the action of how X acts on him. So somehow we have to gather some more information to. So we just looking at M as an R module, we can't recover the Rx module structure on them. Yeah, so I want to collect enough data so that I can recover the Rx module structure. Yeah. So another piece of data is action of X on M. Yeah. So consider this map, that phi from M to M be the linear map which you get by multiplication by X. Yeah. So M going to X dot M. Yeah. Then phi, so phi is a map and it's actually linear because M was an Rx module. So so one of the axioms or module axioms tells you that X dot M1 plus M2 is same as X dot M1 plus X dot M2, and multiplying by some element of R is not going to so R times X dot M is same as X dot Rm, because R times X is same as X times R. Rx is a commutative ring. Yeah. So so phi, let phi be this map, be this. So or rather not let but note phi is a ring homomorphism, is a R linear map, not ring. What am I saying? Is a R linear map. Yeah. Okay. So we have so from this Rx module structure, from this Rx module M, we got two data. Yeah, one is that M is an R module, and another is a linear map from M to M, from the action of X. Now, now what I want to assert is this data is enough to recover the Rx module structure on M. Yeah. So that means given an R module M from and a linear map phi from M to M, it will give me an Rx module M. Yeah, so it will give me an Rx module structure, and the two process will be reversible. Yeah. So maybe I'll try do it in a pictorial way. So Rx module. So first, let me write down the statement which I want to say. So Rx modules M, Rx modules, and maybe so there is a way to go from Rx modules to R modules plus R-linear endomorphism. R-linear endomorphism R module M, and maybe R module M and R-linear endomorphism of M. Okay, so maybe this is not the way to write it down. So there is a good way to write it down, which involves saying categories, but I don't want to worry about this now. Yeah. In endomorphism of the module. Endomorphisms, yeah. Endomorphism, an R-linear endomorphism of the module. Okay. So I gave you a way to go from an Rx module to this, and the point is, and this is reversible. Yeah. So there is a way of saying it in terms of category, but let's not worry about it. Okay, so what is the reverse process? So so maybe conversely, let M be an R module and phi be an endomorphism of M, R-linear endomorphism of M. E belongs to end Rm. Then how do we define an Rx module structure on M? Then for a polynomial, let's say fx, for fx in Rx, define fx dot m. So fx in Rx and m in M, define fx dot m to be, yeah, so I'll need explicitly what it is. Yeah. So an x power n plus an minus 1 x power n minus 1. So I'll need some notation for our polynomial fx. So ai's are little ai's are in R. Yeah. Define fx dot m to be, so if it's just a0, so maybe degree is 0, then you know what to do. Yeah. And then a0 is in R, and we already know what the scalar multiplication is. Yeah. So R dot m. But if it is x, then it should go to, then it should correspond to phi. Yeah. So what you do is consider an and phi power n. So what is phi power n? So it's composition. Yeah. So so should I write it this way? So phi power n means composition of phi with itself. Yeah. So it's an end. Yeah. So maybe I'll write it in the next step. Yeah. And then you evaluate it at m plus an minus 1 times, so an is an element of R, so this makes sense. Yeah. An minus 1 phi power n minus 1 means compose phi to itself n minus 1 times and evaluate it at m. So you get an element of m, then scalar multiplication by elements of R makes sense, and so on. So a1 phi m and finally plus a0 m. Yeah. So this is the definition of fx dot m. In short, see, f is a polynomial, so f of p makes sense. Yeah. So endomorphism is a ring. Yeah. So you can compose, you can take two elements. So if I give you an element, two elements of the ring, you can multiply them and add them and so on. Yeah. So this makes sense. Okay. So in fact, it's an R algebra. So there is a map from R to end Rm. So this makes sense perfectly. Yeah. So an goes to an times identity, and you think of it as that way. Okay. So that is another way of thinking about it. So it's Fp is going to be an is an element of end Rm, and you can evaluate it at m. That is what it is. Yeah. So does that make sense? Is this clear? What is the definition of fx dot m? Okay. So the claim is that this is an R module structure and Rx module structure on M. Yeah. So claim is this makes M into an Rx module. Yeah, so so it's straightforward to verify. So I'm going to, so if you use the second formula, then it's straightforward to verify, because if you have two elements, fx plus fx and gx in Rx, then fx, so maybe it's okay, I'll check one of them. Yeah, so fx gx belongs to Rx, and then fx plus gx action on M, action on M is by definition f of phi, so it's f plus g of f plus g evaluated at phi. So f, and then you evaluate it at M, but fx plus gx is same as, so f plus g evaluated at phi is same as f phi plus g phi, yeah, and then evaluated at M. But these are two linear, f phi and g phi are linear, are endomorphisms of M, so this is same as f phi evaluated at, so linear maps is also an, so the sum in this is defined that way. That's what we saw in home Mn. This was how we defined this sum. Yeah, g phi M, which is same as fx dot M plus gx dot. So so this is one of the axioms, and you can check the other axioms in the same way. Yeah. You just have to plug in phi and see how it plays down. Yeah. So this does make M into an Rx module, and the main claim is that this is reversible. Yeah. So meaning if you start with an Rx module M and cook up this phi, so you get an R module M together with this phi, and then you do this construction back, you get the original Rx module. And so yeah, so this this direction we have more or less done, because so let M be an Rx module, then we get x dot M is this, yeah. So we get an R-linear map, and we go the other way. So remember now we use the same R module structure on M, which we obtained from there, and phi was our linear map. Then and we define this R-linear structure on this. Then note that this R-linear scalar multiplication by Rx in the original thing, and this is same, yeah, because so note that x dot M is precisely phi M, yeah. So and hence x square dot x square dot M is what is going to be x square dot M. This is x dot M by definition of R module, which is x dot phi M. But x dot phi M is going to be phi square M. Yeah, phi of phi M. Yeah, so phi of phi M, which is same as phi square M. Okay. So more generally, fx dot M is going to be f phi evaluated at M. Okay. So so this original Rx module structure and this Rx module and this module structure are same. Yeah. So we do recover this, and you can go the other way as well. So that part I'll leave it as an exercise. So that means if you start with a Rx mod, so if you start with an Rx R module and a linear map, and you build up this Rx modules this way. So maybe I haven't written the conclusion. So let me just write down the conclusion which I want to make. Hence, hence what we get is that so maybe you go, let's give this a name, theta1, theta2. So hence theta1 followed by theta2. If you do this operation on this collection, so this is not a set, so that's why there is a problem, but whatever it is, so you do this operation and come back, and then compose theta1 gives you isomorphic objects. Gives you isomorphic objects. We recover the Rx module. Yeah, so in fact we get not only we get the same object in this case, yeah, because the module is same and even the scalar multiplication is same. Yeah, and you can do the same thing in the other way. So so if you have a R module M and an Rx linear map phi, then you can build up, you can make it into an Rx module this way. And of course, by definition, so maybe by definition of Rx of Rx module structure. So what is the Rx module structure? So now the other way. So maybe now going the other way. Going the other way. We start with R module M and phi in N and Rm. Then Rx module structure on M is defined so that x dot M is precisely phi of M. Yeah, that is how Rx module. So I mean, x dot M, fx dot M is f of phi of M. So if fx is x, that x dot M is phi of M. Yeah. So Rx module structure is this way, and then from this Rx module structure, if you want to get the linear map, and then from this Rx module N, we get the linear map. Okay, the linear map by multiplication by x hence the linear map is phi. Is phi. So we recover the R module M and the linear map phi as well. Yeah. So is this clear? This is a reversible process. Yeah. Any questions? Maybe I belabored it on. So I said a little too much than a little and too less. But I hope it is clear. Yeah. So the two notions are same. Rx modules, an Rx module and an R module together with a linear map. These two concepts are same. Is that okay? Yeah.
Sir,
Yeah.
is this theta1 and theta2, does it form a natural equivalence of categories?
Yeah. So yeah, in fact, it's inverses. So not just equivalence, it's slightly stronger. So you don't even get. So somehow it's an isomorphism of categories.
Okay.
So any questions? Any other question? If so, you should think that the two notions are in some sense the same. Okay. So one can do it in the language of categories, but you'll have to learn the language of categories. And in the language of categories, the statement is slightly stronger in the sense that one also has to look at maps between them and so on. But so if you know the language of category, then one has to check more things, but it's okay. Okay, so we won't worry about that language. It's just at the moment it's not that beneficial to learn. Okay. So if there are no questions, maybe yeah. So maybe we'll take a 5 minutes break. It will give you some time to imbibe this, and then after that we'll move on to maybe Caley-Hamilton theorem. Okay. So
Sir, what part the quiz will contain?
Whatever I covered till today. Yeah. Okay. So let me pause the recording. Thanks. You can speak up, yeah, or someone whoever sees it can speak up. Then we'll save some time. Okay. So so let me just recollect for those who would see the recording. If mu from R to end Rm is injective, then M is called faithful R module. And then we defined annihilator. So this is the definition of when an R module is injective. And then we defined an annihilator. So so given an element small m of capital M, annihilator of small m is all elements of R which kills M. Yeah. So R dot M is zero of the module. And that of course is an R ideal, because if two elements annihilates M, then there's sum and scalar multiple also annihilates. Yeah. So you multiply with anything that will also annihilate. And then annihilator of N is basically those elements of during R which will kill the whole module. Yeah. So R dot M is 0 for all M. And this is intersection of annihilators of elements of this module. And hence, again, this is also an R ideal. And then the homework is show that M is a faithful R module if and only if annihilator is 0. Okay. So let me move to, okay, maybe I'll state the Caley-Hamilton theorem and then move to the other page. Yeah. So what is the Caley-Hamilton theorem? What is the linear algebra version of Caley-Hamilton theorem?
The characteristic polynomial is in the annihilator for the matrix or the linear transformation.
Yeah. So yeah, so if A is a square matrix, so down to earth version is if A is a square matrix, then you can look at its characteristic polynomial. And if in the characteristic polynomial, if you plug in the matrix, then you get some polynomial, some other matrix, yeah, and that matrix happens to be 0. Yeah, that's what Caley-Hamilton. Is that the version you are familiar with? Yeah, so let's
Yes, we have done that.
yeah, okay. So now, so we will do something which is a slight generalization of this thing. Yeah. So since we are learning R modules, we should work with vector space instead of vector spaces. We will work with modules. Yeah? So let R be a ring. And so now we will take the matrix with coefficients in R. Yeah. And A be n cross n matrix with coefficients in R. Yeah. So what is the characteristic polynomial of this matrix? So we define PAX. So this is going to be an, so maybe let's just use capital X for polynomials. So this is defined to be, so characteristic polynomial is determinant of something, yeah? So determinant of xi minus a or a minus xi, depending upon how you were taught, yeah? I'll start this way. But in my notes, I have a minus xi, but it doesn't matter, yeah? So we'll take this, yeah? So this is, so this will give you, so this is this belongs to, so calculation of determinant involves ring operations, yeah? You just multiply things, add things. So this will give you an element of Rx. Yes? So let Px be determinant. Then the statement says that PA of evaluated at A is 0 in, so A is a matrix, yeah, and so so what it is, it's endomorphism of, so it's n cross n matrix, so it's endomorphism of Rn, yeah. So in end Rn. Okay, so this is what Caley-Hamilton theorem says. So we'll prove this, and so there is a completely abstract version as well. So should I do the completely? Yeah, maybe I'll do this, and then maybe one can see the. Okay, maybe I'll state the completely abstract version, and then maybe prove this one, or prove both of them slowly. Yeah. So this is for, so this is the matrix version. So I've just written the matrix version with instead of vector spaces, I've used free modules. Yeah. So the completely abstract version is this one. Let M be a finitely generated R module. And phi be an endomorphism of M, so phi belongs to Ndm. So it's a R-linear map from M to M, such that yeah, so I mean, to use this theorem and in a more reasonable way, we will add some more hypotheses. So from here, I can say that phi satisfies a polynomial. Yeah. is what one can conclude. But I want to assert something more. Yeah, so I'll make some more assumption. So I want to use it to prove something called Nakayama's lemma. Yeah. So phi of M is contained in Im. Yeah, so let's assume that such that phi of M is going to be a submodule of M, and Im is where I is some ideal, where I is an R ideal. Then what we can say, so if you don't assume this, then also you can find a polynomial such that phi is a root of that polynomial. You can't, I mean, since see this, we don't know what kind of, I mean, we don't know explicitly what does linear map do. Yeah, so we'll have to take a generating set and then we can relate it. Yeah, so we don't know what polynomial we'll get. Here we know explicit generating set in the previous one, so we can say which polynomial is that. Yeah? But here we can just say phi will be annihilated by some polynomial, but that's not too difficult to see. Yeah, but what is important is then phi power n plus an minus 1 phi power n minus 1 plus a1 phi plus a0 is 0 for some ai's. So in fact, you can say ai is in ideal I, but you can in fact say ai is in I power I between 1 and I between 0 and oh, okay. So I'll have to write it carefully. So this ai, yeah, so I have to, an minus I is in I power. So maybe I'll write the coefficient differently. So this the constant term has to be in the largest powers. So I've messed it up a little bit. Yeah. So maybe this linear, the first term. So it comes from the proof. So so an minus 1, and this will be an. Okay, so so once you see the proof, you'll know why we have this. Okay, so for I between 1 and n. So this will help us get some mileage. Okay. So so let's do a proof. So I'll do maybe the first version, and the second version proof is similar. So I'll modify it a little. So let me just see the time. Yeah. Okay. So so maybe we'll do the proofs next time. Yeah. So but maybe I can tell you the corollary, which is the Nakayama's lemma of this second version. So I'll just state these three results, and we will prove them next time. So corollary is, so I did talk about local rings, right? Did I talk about local rings? Yeah, I did talk about local rings. Yeah. Rings with only one maximal ideal. Yeah. So let M be a finitely generated module, or so this is slightly yeah. So Nakayama proved it for local rings. And people realize that the proof can be slightly generalized. So the main thing is the idea, yeah, and then someone can obviously generalize it slightly once the machinery is there. Yeah. So let M be a finitely generated module. So I'll write the generalized version module, R module, such that M equals Im for some ideal I contained in Jacobson radical of M. Okay. So if R is local, then it just says that I should be a proper ideal. Actually, that's where this Nakayama lemma is used most. So that's why I mean, I'm not giving too much credit to this generalization. That is the version which is most useful. So if R is a local ring, it says that M should be equal to IM, or maximal ideal times M. So you can take I to be the maximal ideal. So such that M equals IM for some ideal I in Jacobian radical of R, then the conclusion is that M is 0. M is the 0 molecule. Okay. So this is Nakayama's lemma, and then there are some variants of it. But let's do all this proofs next time. Yeah. So it's a bit tight today. Okay. Any questions before we disperse? Yes.
In next is quiz, Tuesday's quiz. Will we have this Nakayama's lemma and Caley-Hamilton theorem?
Yeah, sure. Caley-Hamilton theorem may be there. Nakayama's lemma maybe not.
Okay.
Okay. Yeah. Any other question? Okay, so if there are no questions, maybe we can disperse.